Oh, good afternoon, everyone. I want to welcome you to my lecture today. And of course, I want to welcome you to a new month of November. Okay, today is November 1. And of course, I want to welcome you to a new topic because we are starting chapter 10 today. Uh, and that is going to focus on hypothesis testing. And of course, before the end of the week, midterm 2, okay, midterm 2 practice questions will be released. And I need you to focus on, updates on Canvas for information about the area the midterm 2 is going to cover. Okay. And also to tell you that I have two talks coming up. The first talk will be on November 17 on the workshop organized by Data Science Department, where that workshop centered on economic inequality. And of course, I'm actually going to be talking on the new distribution that I developed, because initially the log normal distribution was used for income, to model income. And of course, I actually going to tell the world using log normal distribution for wage determination or for income could be misleading. And using the idea of statistical theory, I was able to develop a new distribution for that. And of course, a departmental seminar on December 6th that I'm also going to send to, you're going to receive that invitation on announcement section, December 6th. I'm also going to be talking about another topic, developing exponentiated health distribution for one-way analysis of variance in the presence of heteroscedasticity. So I'm going to send you information about that. It's something you're going to gain from, because the knowledge of the theory of statistics will be used. I want to welcome you to this topic. Very important topic, not only in statistics, but all over, whether in psychology, sociology, in every area, they actually conduct hypotheses. So, on the outline, let me also say this. For those of you that are majoring in statistics, there's going to be a meeting, undergraduate meeting with APR on Friday at Ford Hall between 10:15 to 10:50. If you are free, of course, you can actually attend, where you're going to ask some questions. They're going to ask some questions. You're going to have opportunity to ask questions about statistics and with the APR. So I only need 3 to 5 students. If you are interested, you can actually send me a message after this, meeting. Okay, so in the outline, I'm going to walk you through introduction to hypothesis testing, element of statistical test, illustration. Let's get started. I'm first going to start with, what do we mean by hypothesis? Hypothesis is an assertion about the value of a parameter. You remember the other time, we want to figure out what is the true value of a parameter that's unknown. And that was the reason why we were doing what we were doing, like trying to, since we want to figure that out from sample taken from population, and that was why we need estimator, okay, to be able to estimate the value of the parameter. And of course, what we've done before, we got opportunity to identify which estimator work by trying to, investigate the property of estimator, like unbiasedness, efficiency, consistency, and sufficiency. And with the idea of our Blackwell theorem, we're able to identify, estimator with a minimum variance. And if you're not able, if at times the function of sufficient statistic is actually complicated, of course, I also walk you through in the last class the alternative method of estimation that I call the method of movement and the method of maximum likelihood. All of that effort is actually to put in place an estimator that we can actually use to figure out the true value of a parameter. And in the past, okay, I think I told you, statistical inference is about two things. One, estimation. Two, hypothesis testing. I'm going to say that again. Statistical inference is about two things: estimation and hypothesis testing. Before, I've walked you through point estimation and interval estimation. We've done all of that before. That is part of statistical inference. And what we want to do today is a second part of statistical inference. We actually want to figure out the value of a known parameter. But you know what? Because our mind can never be emptied, we may have a particular value in mind. What we have in mind is what we're going to call intelligent guess. Or you know what I mean? That's what I call an assertion about the value of a parameter. But you know what? Whenever we have a value in mind, what we have in mind needs to be tested. We need to be able to verify that through statistical means. If I want to test the validity of a claim, anybody can come with a claim. Okay, we don't want a situation where we're going to live in the world of authoritarianism. Like whatever you tell me, I'm going to agree with you. No way. What I'm going to do, I'm going to investigate. Investigation follow a claim. You get what I mean, right? Okay, so what we want to do now, we give you an opportunity to be able to test how valid is a claim, because we're always going to have a claim. Now, if you want to test how valid is a claim, it means we're actually going to have two types of hypotheses. We're going to have the non-hypothesis. We're going to have the alternative hypothesis. And you know what? We're actually going to have a way, to collect our data, and we need to be able to identify a way of taking decision. What kind of decision do we want? We actually want to see, is there an agreement between theory, okay, and observation? I'm going to say that again. Is there an agreement between theory, because hypothesis will come in form of theory. So we want to see, is there any agreement between the theory and observation, okay? And we'll be able to develop what I'm going to call a criteria that we're actually going to use in taking decision, okay? How should we take a decision? Should we reject or accept, or maybe hold on to our decision? At times in research, not only in research, in the court of law, I've seen a case that have been lingering forever. Okay, they don't know which decision to take, and they're going to declare that as inconclusive. So in statistical theory and statistical framework in general, we got a way to actually test the validity of a claim. Okay, and that was why I was trying to say here, okay, a scientist actually poses hypothesis concerning one or more parameter, okay, and the equal specified value. Now, this guy, actually, if I want to test the validity of a claim, then I need to sample the population. I need to go back to the population, take a sample. But what will trigger me going to the population? Because that have been a claim. Investigation follow a claim. Does that make sense? Okay, now, and compare our observation with the hypothesis. If the observations disagree, with the hypothesis, the scientists reject it. So which means only way we reject is when observation disagree, and we normally pay attention to the non-hypothesis. It's either the non-hypothesis is rejected or we fail to reject it. In a situation where we're going to reject the non-hypothesis, that is actually telling, no, there's a disagreement between, your observation and your hypothesis. Because if there's an agreement, we're actually going to what? Fail to reject the non-hypothesis. So the non-hypothesis, the alternative hypothesis, these are two hypotheses that are actually conflicting, and they are mutually exclusive. It's only one that we're going to take at the end of the day. Okay, if not, the scientists will conclude, okay, either that the hypothesis is true or that the sample did not detect the difference between the real and hypothesized value of the population parameters. We got a lot of examples here that I'm actually going to talk about. Okay, maybe somebody here, a medical researcher, hypothesized that, oh, maybe he has discovered a new drug that is more combative than the conventional drug. And if we want to test the claim, what we're going to do is we're going to take a sample of patients that are suffering from that disease. We're actually going to create two groups. Okay, we're going to create two groups, and the two groups will have equal chance of receiving any patient, because we're actually going to use what I call the principle of randomization in assigning patient to the group. Okay, one group is actually going to be called a placebo group, and the other group is going to be called the experimental group. The placebo group is going to be those patients that will receive the conventional, and why the other group is actually going to be the experimental group. And at the end of the day, okay, we actually going to compare the number of patients that recover from the disease, after being subjected to the two different drugs. Now, I want to tell you, the world actually wake up to an ugly incident in 2020. Okay, we got the COVID, I'm talking about the COVID pandemic. But, after what I'm going to call shut down, loss of jobs, no social interaction and stuff like that, I want to say that was a good news in December 10, 2020, when you check the New Journal of Medicine in the state of Massachusetts, in the United States, there was an article published. And that very article was actually called Safety and Efficacy of the BNT162b2 mRNA COVID-19 vaccine. And this was, in the article, they actually, I'm actually referring to Pfizer vaccine. They developed a vaccine and they petitioned those, they selected at random, a good number of people, and they actually assigned them to two groups. The first group received placebo. Placebo is nothing. And the second group actually received the Pfizer vaccine. And, they use about 40,000 for each group. And what they do is, I think they actually give them like 2 doses. You remember, then you actually going to get 2 doses, and that 2 doses will be within 21 days apart. Those in the placebo group also receive a drug, but that is nothing, doesn't have any effect. And those in the experimental group actually receive, Pfizer vaccine. And in the end, they compare the numbers of, the 2 groups were subjected to COVID, and, they actually want to see what is the, how able, they really want to know how those who are vaccinated with COVID vaccine will be able to prevent the occurrence of COVID. And why is it called BNT162B2 is because out of the 40,000 in the about 40,000 in the placebo group, 162 catch COVID, okay? And in the experimental group is only 8. And they look at that, and the Pfizer was able to derive 95% efficacy. Okay, they tell the world, their vaccine, okay, has 95%. So, that is an experiment, an hypothesis testing was actually conducted, and they were able to convince the world, and that was why they submitted requests to the what do they call, I think um those in terms of Food, Drug, and Administration in the United States, where they are seeking emergency use of the vaccine. Not only that, between, the Center for Disease Control, I think they observed the weight of Americans between 1960 and 2002, and they realized Americans have gained weight in 2002. Okay, and the average weight for me was 191. Do you know that in 2006, we can actually hypothesize that, the average weight could be more than 191. If we really want to investigate that, it's going to be through hypothesis testing. There's a lot, I want to tell you, hypothesis testing can actually be conducted in all field where you're actually seeking to, test observation, want to compare observation with hypothesis. Do they have any agreement or not? Okay, so hypothesis testing is very, very crucial. Okay, now take a look at this. A quality control engineer may hypothesize that a new assembly method produces only 5% effective items. No matter how we do, in company, there's always going to be defective. Okay, 100% of what they produce would not be a defective free. You get what I mean? There's always going to be defective. And this guy may claim that, okay, the method of assembly, my method, we only produce 5%. Then that 5% is an hypothesized value that can be tested. Does that make sense? Okay, an educator may also claim that the two methods of teaching, reading, are equally effective, and we can decide to say, no, they are not. Okay, we can actually investigate that through hypothesis testing. And of course, a political candidate may actually claim, that a plurality of vital favor is election. That can also be tested as well. And of course, if I want to test, I'm actually going to start with data. I need to go to the population of interest. Okay, when I go into population of interest, I'm actually going to collect data. Okay, when I collect data, then I need to be able to put in place what I call a test statistic. Okay, now with the test statistic, then I will be able to also put in place what I call a rejection region. If my test statistic actually fall in the rejection region, then I'm actually going to reject statistic. Okay, now with the test statistic, then I will be able to also put in place what I call a rejection region. If my test statistic actually fall in the rejection region, then I'm actually going to reject the null hypothesis, otherwise I don't reject. And that's why we're going to conduct a test, and it's actually going to be, should we reject or not? Because there are two hypotheses before us. Now, let us now go into the element of a statistical test. Okay, now when I'm talking about element of statistical test, I may actually want to talk about what are the procedure of statistical tests. Okay, and how am I going to set up a rejection region? How am I going to set up my test statistic? How am I going to take a decision, okay, whether I should reject or not, or withhold my my decision? And can I also figure out the probability of making wrong decision? We are not perfect. I told you the other time. We live in a stochastic world. We actually want to capture reality using a model. Whatever technique we use, our model cannot capture exact reality. There's always going to be error. So in every research, you need to be able to what is the probability of committing error? And what we always want to do is to minimize the probability of committing error. Okay, Of course, I'm going to walk you through all of that. Now, take a look at this. We're talking about a political candidate, John. He claimed that we actually gain more than 50% of the vote in a city election. When you gain more than 50%, okay, based on the law of the state, electoral law of the state, probably is going to be the winner. Okay, now if we do not believe John's claim, okay, because that's not a crime, it's normal. We may not believe what he say. Okay, if we do not believe John's claim, okay, we might seek to support the research hypothesis, okay, that the John is not favored by more than 50% of the electorate. Okay, so which means we're actually seeking the alternative hypothesis now, going against John. The non-hypothesis is going to favor John. Does that make sense? Okay, now, which means the true value of a parameter is unknown. What would be the true value of a parameter now is going to be the true proportion of voters favoring John. We don't know that. But John has a certain value in mind. Okay? I don't know why he has that confidence. Maybe because he was actually looking at polls. Exit polls, or, there used to be polls conducted ahead of election. Okay? I don't know. Maybe that is what he rely on. Now, because of that, we're actually going to have two hypotheses under investigation. One is going to be the non-hypothesis. We're actually going to set that at 50% because that is going to be the minimal requirement. And why the alternative? The one we are seeking right now, we're actually going to be calling alternative. We are actually going against John's claim. So going against John's claim now is P less than 0.5. Is there any question about that? Any question? Okay, now, what is the goal here? The goal is we actually wish to support the alternative hypothesis by showing lack of support. The lack of support for John is actually going to be the inverse. It's actually going to contradict the claim of Jones. Okay, and that is why is that in research we always looking for significant result. Like, having a significant means, I've rejected the non-hypothesis. Okay, what are we going to do now? What we're going to do, we want to set up an investigation. We have an hypothesis right now. This is synonymous with what happened in the court of law. In the court of law, they're actually going to start by introducing the case, and they're going to ask from the accused person, and they're going to be two hypotheses before the court. It's either the accused person is guilty or not. Does that make sense? Okay, now what is going to be the next thing they're going to do is to start calling for witnesses. That they are not going to call everybody in the scene, in the crime scene. They're only going to select a sample. So right now, in order to investigate the Jones claim, we're actually going to select a sample of voters from from that population, and right now we are selecting a sample size of 15. Now, when we select a sample size of 15, don't forget the other time I told you, if this guy is a false person, it's either a support John or not, and that is going to follow Bernoulli distribution, two possible outcomes, and, we're actually going to label those who favor John 1 and the other one 0. Does that make sense? And what are we going to be seeking? We actually need Y. We need this guy who's going to be summation Y. We need a summation Y. And what is going to be the summation Y? If Y follow Bernoulli distribution, summation Y will follow binomial. Does that make sense? Now, when summation Y follow binomial, right now, this is what we have. Binomial, N is 15, but we don't know P. P is going to be the true proportion of those who actually favor June. Now, because of that, we need what I call test statistic. Test statistic is what we call TS. So the test statistic, that will be based on the observed value. what we observe now, the test statistic, is going to be based on the observed value of y, okay? And that will enable us to make a binary decision. And you know what we're going to do? This is what we're going to do, okay? We're actually going to create that ourselves. Like, we need these two situations where y is small, okay, and where y is not small. If y is small, okay, like for instance, if y equal to 0, okay, and because of that, we can actually say, okay, let us just assume that if this happen, that k now out of 15, because we need to four of us like agree, okay, you know what we're going to do? We're actually going to reject Jones' claim if y is less or equal to a particular value that we are going to be the one that will set it up. We could call that our k2. If I have two individuals out of 15, two individuals out of 15 that only favor you, then it means we're going to reject you. Because we're going to reject your claim, because 2 out of 15 is very far away from 50%. Does that make sense? So we're actually going to be the one that will decide that. Okay, and that was why I said here, if y is less or equal to k, then we reject the null hypothesis. Okay, when we reject the null hypothesis, then we're actually going to favor the alternative. Does that make sense? And if y is greater than k, y greater than k means y is not too small, then we're actually going to fail to reject the null hypothesis. Failing to reject the null hypothesis, then it means Jones is right. Does that make sense? Okay, so this is y less or equal to k or y greater than k. If you take a look at that now, it's more or less going to be, we're actually going to create what I call a rejection region. Okay, now because of that, I'm actually coming here. Like I said, in order to be able to take our decision, okay, to take our decision, we need to be able to set up a rejection region. Take a look at that. It's 0, 1, 2. Okay, our rejection region is y less or equal to 2. What is it meaning? Y less or equal to 2? Oh, out of 15, if I can only find 2 that support Jones, I will reject Jones' claim. Does that make sense? That is the rejection region that we create. Does that make sense? And we don't just create a rejection region. We're going to put into consideration, okay, the level of error, which I'm still going to show you, okay, a connection between rejection region and the probability of committing error. What do I say? What do I mean by that? Committing error. What I mean by that? Oh, maybe taking wrong decision. That's what I mean. Okay, now because of that, we're actually going to have a definition. Okay, what I call the test statistic. What do we mean by test statistic? What do we mean by rejection region? Of course, a test statistic is actually a function of the sample on which the statistic decision is based. While the rejection region will be the set of value for the test statistic for which the null hypothesis is to be rejected. And like I said, we're going to be the one that will decide that. Okay, like for instance, this, the other time I said y less or equal to k, we are going to be the one that will determine the k. And that very k is going to be a value within the sample space of 0 to 15 here. Don't forget the sample size here is 15. Now, we have a way to take decision. Okay, and taking decision now, if the test statistic lies, this guy means lies in the rejection region, then we're going to reject H naught. We only reject when the test statistic value lies in the rejection region. Okay, who is going to create the rejection region? We. Does that make sense? Okay, then if TS does not lie, like if the test statistic does not lie, then we're going to fail to reject H naught. Any question? Go ahead. Oh, okay. I should clarify why I choose y less or equal to 2. I just choose that hypothetically. I choose that for convenience. You say what? Exactly. But we don't just choose. I like your question. We don't just choose. I'm going to show you, I'm going to walk you through reason why we don't just choose a number. We choose a number, okay, with intention of minimizing type 1 error rates. Does that make sense? Minimizing. When I say I'm still going to tell you type 1 error rate in research. We got 2 error, type 1 error, type 2 error. We're going to choose our critical region, with the intention of minimizing those errors. Does that make sense? Okay. Now, I want to walk you through the element in the procedure now of testing hypothesis. Of course, like I said, you're going to state, you need to specify your non-hypothesis, your alternative. Then you need to tell the world your test statistic. Then you're going to tell the world your regression region. Now, look at your question here. Hello, can you see me? Can you hear me? Hello, can you hear me? The guy that asked the question. Which values of K, okay, specify a good regression region? Which value of K? You asked me the other time, why do I just choose 2, right? Okay, we don't just choose value. We need to be able to answer a question. Which value of K specify a good regression region? We want to have a good regression region, and that is the reason why we don't just specify a value for that. There's going to be something that we're going to put into consideration before we do that. Does that make sense? And what is that? Use errors to measure the goodness of tests. You see that? We're going to use error to measure the goodness of tests. I'm writing an article now. I'm not done. The article, I actually want to make a recommendation to any courts, anywhere in the world. Whenever you decide a case, tell the world, what is your probability of making error? Does that make sense? Because the court is not perfect. They need to tell the world, okay, what is the probability of making error? Do you know how they can decide on the probability of making error in a court? Okay, now, how many of, if a court decide a case, and somebody now appeal to higher court, how many of such judgments were declared null and void? Does that make sense? That is how the courts will know the probability of them making error. Okay, now, because of that, that will lead us, determining the values of K now in our rejection region, that will lead us to the types of error. I told you the other time, statistics is like a story, right? Now, we're going to look at the types of error, because if I want to know what is the goodness of fit of a test, then I need to measure the error. Of course, in statistics, if I want to tell how good is my model, then I need to be able to revisit whether assumption hold. And assumption in statistics centered on the error. Does that make sense? Okay, now take a look at this now. We got it. We got state of nation or state of nature and the decision you took. We want to see is there, all nature knows the truth. But do you know what we want to do as researcher? We want to see whether we can actually predict the mind of the nature. Okay, take a look at this situation where we actually fail to reject H0. And if H0 is true, H0 is actually true, and we fail to reject that, that's a correct decision, right? That's a correct decision, right? H0 is true, and we didn't reject it. Okay, that is where we mark here. This guy. Okay, take a look at this guy. We reject HO when HA is true. That's another correct decision. Does that make sense? We reject HO but do you know the issue we normally have in terms of the error? Take a look at this guy here. According to the nature, HO is true, but what happened? We reject it. That's an error. What is the name of that error? We call it type 1 error. Does that make sense? And that type 1 error is symbolically represented as alpha, which is this guy here. Alpha equal probability of rejecting HO given that HO is true. That's an error. Okay, I've seen situation whereby accused person by nature, he didn't commit the offense, but is in jail, is convicted. And we see situation whereby somebody who committed the offense has been declared the charge, have been the charge and acquitted. And that's why I used to tell people criminal at times they live around us. Why? Innocent person at times they are in jail because of the error committed by the courts. We also have this error in research. So we call that type 1 error and type 2 error. Okay. The type 2 error is when we fail to reject the null hypothesis. Okay. When we fail to reject the null hypothesis when the alternative is actually true. Okay. We call that alpha and beta. Okay. Now you know the error in research now. And that is why in every statistical test, we normally want to tell the word alpha. The alpha is a level of significance. It's also the probability of a type 1 error. Does that make sense? Okay. Now, we want to go back into the example of June. We choose a sample size of 15. And the hypothesis that we actually want to, these are the method, the procedure of conducting hypothesis testing. We need to state the known and the alternative. Then we need to decide what is going to be the test statistic. The test statistic in this case is going to be Y, which is going to be the sum of the responses. Don't forget, individual has a response 0, 1. Does that make sense? Okay. Now, and we need to tell the world what is our rejection region. Here now, I'm actually choosing 2, K to be 2, but we're not just choosing K, okay, in the rejection region. We need to choose the values of K that will minimize the error of hypothesis. Does that make sense? Okay, how are we going to do that? You're going to see now. Now, take a look at this. Please, I needed to pay attention now. We want to go theoretical. Need to pay attention now. Now, which means if I choose this, if I choose K to be 2, which means in my rejection region, if Y less or equal to 2, 2 out of what? 2 out of 15. If 2 out of 15 only say we're going to favor John. Does that make sense? Okay. If the test statistics fall in the rejection region, which means we're actually going to reject John's claim. But if I need to be able to tell the world I got the best rejection region, how am I going to show the world? If I want to show the world I got the best rejection region, then I need to also show the world my level of significance that I also call the probability of type 1 error. What am I going to do? I need to compute that. I want to compute the probability of type 1 error. Okay. And what is that probability? The probability of the test statistic fall in the rejection region, given that the null hypothesis is true. If I want to do that, and what is the state space of my rejection region, Y less or equal to 2, what does it mean? 0, 1, 2, right? 0, 1, 2. And don't forget Y follow binomial distribution. So which means I need to find this guy using the binomial formula, where I'm going to go from 0 to 2, 15 you understand binomial formula. And in the end, oh my God, in the end, this probability is very, very small. Okay, by choosing this guy now, okay, give me 1 second. By choosing this guy now, okay, we subject ourselves to a very small risk. And that risk is 0.4% of concluding John will lose if in fact he wins. Any question? Which means the rejection region we are choosing to us makes sense, right? But we are not going to only focus on type 1 error alone. We also need type 2 error. Now, we're going to go and compute type 2 error. Computing type 2 error, I want to find beta, which is the probability that the test statistic does not fall in the rejection region, given that HA is true. Now, I'm going to go against, initially, For the null hypothesis, it was y less or equal to 2. For the alternative, I'm actually going to go against y less or equal to 2, which is going to be 1. I'm actually going to go for y greater than 2. What is y greater than 2? That is 3 and above. That was why you have this guy here. Please follow what I'm presenting now. Okay, take a look at this. That's why I'm having this now. Now, the probability of y greater or equal to 3. I mean, greater or equal to 3. Given that, I'm not going to use what I have in the null hypothesis. What in the alternative is going less than, right? Less than is 0.5. Then I need the values of P less than is 0.5. The examiner is going to give you. And that was why here. Take a look at this. Do you see that? I said, is our test equally good in protecting us from concluding that John is a winner if in fact he will lose? Which means we want to find the probability of type 2 error. Now, I said, suppose that he will receive 30% of the votes. That would be the P we're going to use. Is 30% of the vote is less than what you hypothesize. Does that make sense? That is what I'm actually going to use now here in the binomial again. I'm going to go into the binomial again, but this time around, I'm going to go from 3. Don't forget, in the rejection region was less or equal to 2. Then the other one is supposed to be opposite of that, which should be greater than 2. Greater than 2 means 3 or more, right? Take a look at that. Oh my God, the type 2 error is so high. Look at that. The type 1 error is very small, but the type 2 error is very, very large. There is a problem here. Does that make sense? Because now, and that was why I said, if we choose the rejection region, okay, if we choose the rejection region to be this, our test will usually lead us to conclude that John is a winner, okay, even if P is as low as 0.3, okay. Now, when you take a look at what I have now, why the type 1 error is very small, but the type 2 error is very, very large. But let me tell you this. Statistically speaking, when you make an attempt to reduce type 1 error, the type 2 error is going to go up. Does that make sense? And what do we now need to do? Now, for instance, you can do this. Let us calculate beta if John will receive only, we calculate beta. If John will receive only 30%, we got that as type 2 error. What of if it's going to receive 10%? When that thing goes down, what happened? The beta we're going to compute will be, we're going to go down. Now, take a look at this. We repeated that, and in the end, we're going to have, so in a situation, our observation here is when we make an attempt, to improve on type 1 error, it will affect type 2 error. When we make an attempt to improve on type 2 error, it will affect type 1. Okay? Now, and that was why I said here, example 10.1 through 10.2 show that the test using rejection region y less or equal to guarantee a low risk of meeting type 1 error, which was 0.004, but it does not offer adequate protection against type 2 error because the type 2 error was so high, 0.8 something. Now, how do we improve our test then? Situation where type 1 error goes down and type 2 error goes up. Okay, and the answer is we need to be able to what? Change the rejection region to be able to balance the type 1 and type 2. They need to be balanced. And what are we going to do? If you take a look at the picture here, this is the initial range of type, of the rejection region. We can actually increase it. Instead of using y less or equal to 2, we can increase the k. Does that make sense? And when you increase the k, then you are decreasing. Don't forget, when you are increasing, the rejection region, then you are decreasing acceptance region. Does that make sense? And that was what we're trying to say here. Okay, if you take a look at this, alpha star is the probability of is an adjusted probability of type 1 error. After you are now using new rejection region, a very big area. Okay, and that will be greater than the conventional one. Does that make sense? You know, the unadjusted one was very, very small because we're using very little space. Now, when the space is now extended, okay, we're actually going to increase this in a way. Okay, and this guy, what do you want to do to type 2 error? You know, to reduce it. So when you want to create a balance, your alpha, your type 1 error is going to go up a little bit, while the type 2 error is going to go down. That is the adjustment we're talking about. That's why the beta star is going to be less or equal to that. Okay, I need you to see this now. Because of that, we are now changing K from 2 to 5. We now want to compute what is going to be our alpha, and we're going to compute what is going to be our beta. If you follow what you've done before, now take a look at this guy and take a look at this guy. What has happened? Take a look at the two. From 0.004 to 0.151, type 1 error goes up. What happened to type 2? Oh my God, the type 2 error goes down significantly to 0.278. You know why you have that? Because you modify your rejection region. Does that make sense? When you modify rejection region, like increasing the values of K, the type 1 error will increase, but the type 2 error will go down significantly. Okay, now the question now is, oh, we cannot eat our cake and have it. We make an attempt to reduce type 2 error, but type 1 error also goes up. Then what are we now going to do? It's for instance, if I want to reduce both, then you should be ready to take more sample size. Increase sample size. That has taken us to what we've done before. Law of large number. When you increase your sample size, what's going to happen, right? Your sample statistic will converge to the true value of parameter. So if you want to increase, if you want to reduce both type 1 and type 2 error, then you actually go to increase the sample size. Does that make sense? Okay. Now, lastly, I'm gonna have this as my last example. Oh, give me 1 second. I think somebody is. Oh, okay. Somebody is attending this lecture on Zoom with me right now. Or somebody said, can you clarify the intuition behind K? I think I've just said that. I believe you. Oh, somebody said, I understand now. No worries. Okay. Thank you so much. Okay. Now, I want to go into a last example now. We got 3 balls in the box. And they told me it's a red, and it could be red or white. Okay. And we are interested in the numbers of red. Because I don't have access to the box, okay, my parameter now is actually going to be the numbers of red. Okay, if I draw 2 without replacement, okay, because each of them is going to be a binary process. Why? It's going to be a binary process. Okay, let's say we want to test hypothesis that the numbers of red is actually 1 or less than 1, and the alternative is going to be greater than 1. Okay, now testing that hypothesis now is like, I got something in mind. Oh, okay, the numbers of red may be 1 or less than 1, and somebody is going to say no, it could be greater than 1. That is the alternative. Now, because I'm choosing 2, my test statistic will be y1 plus y2. y1, y follow Bernoulli. Then I'm going to tell the world my rejection region here, at least 1 out of 2. At least 1 will be 1 and 2, right? Okay, reject H0 when there's at least 1 red ball in the sample. How many samples do we choose? 2. If I have at least 1, I will reject the null hypothesis and say, no, it's going to be number of red is going to be greater than 1. Okay, I need to set up a table. where I'm going to consider the probability of the join. And I'll show you on Monday. Take a look at that. Okay. Now, this is the probability of the join considering state of nature. And of course, I'm going to get what is the probability of y equal to 0, y equal to 1. And that I'm just going to add up. Okay. I'm going to add up to be able to get this. Then I'll compute my type 1 error, just like what I used to say. I can also compute my type 2 error. Okay. And what if I change my rejection region to just 2? Then I can also compute my type 1 and type 2 error. The takeaway, if you really want to know how best is your rejection region, you need to analyze errors, the type 1 and type 2. Oh my God, my time is up. This is where I'm going to stop today. Is there any question before I go today?